Hello and welcome to our astronomy course. Okay, so today we are going to study uh, the lecture number 8, and the topic of this lecture, the formation and structure of stars. Okay, now you already know that the stars which you see tonight are not eternal. The stars are the same stars your parents, grandparents, and great-great-parents saw. Stars change hardly at all in a human lifestyle. But they have a life cycle of their own. Stars are born and stars die. And this lecture begins that story. In this lecture, you will see how gravity creates stars from the thin gas of space, and how nuclear reactions inside stars generate energy. You will see how the flow of that energy outward toward the surface of the star and balances gravity and make the star stable. In the next module, you will complete the story of stars as they exhaust their fuels and time. How can astronomers know what stars are, like when they can't see inside them and don't live long enough to see them evolve? The answer lies in the method of the science, by constructing theories that describe how nature works and then testing those theories against evidence from observation. Scientists can unravel some of nature's greatest secrets. They can even understand the origin and structure of the star. The key to understanding star formation is the correlation between young stars and clouds of gas and dust. Where you find the youngest groups of stars, you also find large clouds of gas and dust. This should lead you to suspect the stars formed from such clouds, just as raindrops condense from the water vapor in a thundercloud. Thundercloud. But how can this cold clouds contract, heat up, and become stars? You know, it is a common misconception to imagine that space is empty, a vacuum. In fact, the space between the stars is not empty, but is filled with low-density gas and dust called the interstellar medium. About 75% of the mass of the gas in the interstellar medium is hydrogen, and 25% is helium. There are also traces of carbon, nitrogen, oxygen, calcium, sodium, and rest of heavier atoms. Roughly 1% of the mass is made up of microscopic dust particles called interstellar dust. The dust particles are tiny, about the size of the particles in cigarette smoke, mixed with or coated with frozen water. The average distance between dust grains is about 10 up to 100 meters. Imagine. These interstellar gas and dust are not uniformly distributed through space. It consists of a complex tangle of cool, dense clouds pushed and twisted by its current of hot, low-density gas. Also, the cool clouds contains only 10 to 1,000 atoms per cubic centimeter. This is fewer than any vacuum in a lab on Earth. Astronomers refer to them as dense clouds in contrast with the hot, low-density gas that fills the spaces between clouds. That thin gas has a density of only about 0.1 atom per cubic centimeter, which is the same as one atom in every 10 cubic centimeters. The preceding two paragraphs describe the interstellar medium, but you should not accept these facts blindly. Science is based on evidence, so you should demand to know what observational evidence supports these facts. How do astronomers know there is an interstellar medium? And how do they know its properties? In some cases, the interstellar medium is easily visible as clouds of gas and dust, as in the case of the Great Nebula in Orion, an object you can see with your unaided eye. Astronomers call such a cloud a nebula from the Latin word for cloud. Such nebula, plural, are clear evidence of an interstellar medium. Study three kinds of nebulae are noticed three important points and four new tests. Thus, emission nebula are produced where very hot stars excite clouds of low-density gas to emit light. The clouds are mostly hydrogen gas ionized by the light from the hot star. So, the nebula are sometimes called HII region. Second, where slightly cooler stars illuminate gas clouds containing dust, you see reflection nebulae, which provide evidence that the dust in the clouds is made up of very small particles. Third, dark nebula are produced where dense clouds of gas and dust are silhouetted against background regions filled with stars or bright nebulae. If cloud is not too dense, straight starlight may be able to penetrate it. Stars can be seen through these clouds, but the stars lose diameter because the dust is the cloud scatters some of the light. Because shorter wavelengths are scattered more easily than longer wavelengths, the redder photons are more likely to make it through, so the stars look slightly redder than they should, an effect called interstellar reddening. Let's look at this slightly. This is the same process that makes the setting sun look redder. Okay? Distant stars are dimmed and reddened by interviewing gas and dust. Clear evidence of an interstellar medium. And near-infrared wavelengths, stars are more easily seen through the dusty interstellar medium, because those longer wavelengths are scattered less often. The thin gas and dust fill the space between the denser nebula. You can see evidence of that in the spectra of distant stars. As you can see in this figure A on the upper part of this slide. As starlight travels through the thin gas of the interstellar medium, gas wavelengths producing narrow interstellar absorption lines. You can be sure these lines originate in the interstellar medium because they appear in the spectra of O and B stars. Stars that are too hot to form calcium and sodium absorption lines in their own atmosphere. Also, the narrowness of the interstellar lines indicate they could not have been formed in the hot atmospheres of the star. Recall that in a hot gas, the atoms move rapidly, and the Doppler shift of the different atoms smear the spectral lines, making them broad. The narrow lines must have formed in the interstellar medium, where gas atoms travel very slowly. The extremely narrow widths of these lines show that the gas of the interstellar medium is very cool, in really 10 to 50 Kelvin only. Often multiple interstellar lines appear with slightly different Doppler shifts because the light from the stars passes through a number of gas clouds in its way to Earth, as you can see in figure B on the medium of this slide. Observations at non-visible wavelengths provide valuable evidence about the interstellar medium. X-ray observation can detect regions of very hot gas apparently produced by exploding stars, and infrared observation can detect dust in the interstellar medium. Also, interstellar dust grains are very small and very cool. There are a huge number of grains in a cloud, and each grain emits infrared radiation at long wavelengths. If the gas is cool enough, molecules can form, and some molecules in the cold gas emit in the infrared. So, infrared observations can detect very cold clouds of gas, right? Ultraviolet observations have been able to map the distribution of hydrogen in space and reveal that the sun is located just inside a cavity filled with hot gas. Furthermore, radio astronomers can study the radio emissions of specific molecules in the interstellar medium, the equivalent of emission lines in visible light. And this figure shows regions where hot stars have inflated bubbles of intensity hot gas that push into the interstellar medium and cause the condensation of dust. The hot gas is detectable at X-ray wavelength, and the dust is easily absorbed in the infrared. New stars can be born where the gas and dust are compressed. There is no shortage of evidence that there is an interstellar medium. Now you can look for evidence linking clouds of gas and dust with the birth of stars. To study the formation of stars, you must continue to compare theory with evidence. Theory predicts that over time, the combined gravitational attraction of the atoms in a cloud of gas will draw the gas inward, pulling every atom toward the center. But not every cloud will collapse and form stars. The thermal energy in a cloud resists collapse. Are you agree with me? Okay, let's go on. Temperature is a measure of the motion of the atoms or molecules in a material. In a hot gas, the atoms move more rapidly than do those in a cool gas. The interstellar clouds are very cold, but even at a temperature of only 10 Kelvin, the average hydrogen atom moves about 500 meters per second. This thermal motion would make the cloud drift apart its gravity, were too big to hold it together. Other factors can help the cloud resist its own gravity. Observations show that clouds are turbulent places with currents of gas pushing through and colliding with each other. Also, magnetic fields in clouds may resist being squeezed. These three factors, thermal motion, turbulence, and magnetic fields, resist gravity. So only the densest clouds are likely to contract. The densest interstellar clouds contain from 110 in power 3 to 10 in power 5 atoms per cubic centimeter. Include from a new founded thousands of a few million solar masses and have temperatures as low as 10 Kelvin. In such clouds, hydrogen can exist as molecules of hydrogen, H2, okay? And rather than an atoms. These dense clouds are called molecular clouds, and the largest are called giant molecular clouds. Also, hydrogen molecules cannot be detected by radio telescope. The clouds can be marked by the radio emission of carbon monoxide molecule, CO, okay? Present in small amounts in the gas. Stars form in these clouds when the densest part becomes unstable and contract under the influence of their own gravity. Most clouds do not appear to be gravitationally unstable and will not contract to form stars on their own. However, a stable cloud colliding with a shock wave, the astronomical equivalent of a sonic boom, it can be compressed and disrupted into fragments. Theoretical calculations show that some of these fragments can become dense enough to collapse under the influence of their own gravity and form stars. Let's look at this slide, please. Shock waves are necessary to trigger that star formation, and space is filled with shock waves. A shock wave is a sudden change in gas pressure, and a number of processes can produce them. The sudden blast of light, especially ultraviolet radiation from a newborn massive star, can ionize and drive away nearby cars, forming an expanding shock wave. The collision of two interstellar clouds can produce a shock wave too. Supernova explosion, it means exploding star, will be described in next module, produce powerful shock wave. Examples of some of these processes are shown in this slide. Also, these are important sources of shock waves, the dominant trigger of star formation in our galaxy, and maybe the spiritual arms themselves. In second lecture, your fall semester, do you remember it? Okay. You learn that our galaxy contains spiral arms. As interstellar clouds encounter these spiral arms, the clouds are compressed and star formation can be triggered. Once begun, star formation can spread like a grass fire. Astronomers have found a number of giant molecular clouds in which stars are forming in a repeating cycle. Both high mass and low mass stars form in such a cloud, but low mass stars are not powerful enough to keep the star formation going. When massive stars form, however, their intense radiation and eventual supernova explosions push back the surrounding gas and compress it. This compression in turn can trigger the formation of more stars, some of which will be massive. And thus, a few massive stars can drive a continuing cycle of star formation in a giant molecular cloud. A collapsing cloud of gas breaks up because of instabilities in the contracting cloud and produces from 10 to 1,000 stars or even more. Stars held together in a stable group by their combined gravity are called a star cluster. An association is a group of stars that are not gravitationally bound to one another. The stars in an association drift away from each other in a few million years. The youngest associations are rich in young stars, including O and B stars. To follow the story of star formation further, you need to concentrate on a single fragment of a collapsing cloud as it forms a star. You might be wondering how the unimaginably cold gas of an interstellar cloud can heat up to form a star. The answer is gravity. Once part of a cloud is triggered to collapse, gravity draws each atom toward the center. At first, the atoms fall unopposed, and they hardly even collide with each other. In this free fall concentration, the atoms pick up speed as they fall until, by the time the gas becomes dense enough for the atoms to collide often, and they are traveling very fast. Now collisions convert the inward velocities of the atoms into random motion. Recall that temperature is a measure of the random velocities of the atom in a gas. The inward collapse of the cold gas converts gravitational energy into high random velocity, causing the temperature of rise. The initial collapse forms a dense core of gas, and as more gas falls in, a warm protostar develops very deep in the dusty gas. A protostar is an object that will eventually become a star. When a star or protostar changes, it is said to evolve. And you can follow that evolution in the A chart diagram. As the object's temperature and luminosity change, its location in the HR diagram shifts, and you can draw an arrow called an evolutionary track to represent these changes. Because protostars start out very cool and very faint, and you must extend the HR diagram to the right part to include very low temperature. And this slide, which includes temperature below 100 Kelvin, you may see in this part, shows the initial collapse of one solar mass cloud fragment as its temperature rises to more than 1000 Kelvin. The exact process is poorly understood, in part because the dusty clouds hide the protostar from sight during its contraction. If you could see a developing protostar, it would be a luminous red object a few thousand times larger than the sun. Imagine how massive diameter. And you would plot it in the red giant region of the HR diagram. It is not, however, a real red giant, and it is invisible inside its dusty cloud. The hot gas inside the protostar resists gravity, and the star can continue to contract only as fast as it can radiate energy into space. Also, this contraction is much slower than the free fall concentration. The star must continue to contract because its interior is not hot enough to generate nuclear energy. Through its contraction, the protostar converts its gravitational energy into thermal energy. Half of this thermal energy radiates into space, but the remaining half rises the protostar's internal temperature. As the internal temperature climbs, the gas becomes ionized, becoming a mixture of positively charged atomic nuclei and free electrons. When the center gets hot enough, nuclear reactions begin generating energy, and the protostar halts its contraction, and having absorbed part of its cocoon of gas and dust and blown away the rest, and it becomes a stable main sequence star. The time it takes for a cool interstellar gas cloud to contract the main sequence depends on its mass. The more massive the protostar, the stronger its gravity, and the faster it contracts. Let's look at this figure. The sun took about 30 million years to reach the main sequence, but a 15 solar mass star can contract it only 160,000 years only. In converse, a star over 20% solar mass takes 1 billion years to reach the main sequence. So far, the story of the formation of a star from the interstellar medium has been based on theory. By understanding what the interstellar medium is like, and by knowing how the laws of physics work, astronomers have been able to tell the story of how stars form. But you can't accept a scientific theory without testing it. And that means you must compare the theory with the evidence, right? And that constant checking of the theory against evidence is the distinguishing characteristic of science. So it is time to carefully separate theory from evidence and ask how much of the story of star formation can be observed. In astronomy, evidence means observation. So you should expect astronomers to have observations that confirm their theories of star formation. Unfortunately, a protostar is not easy to observe. The protostar stage lasts for less than 0.1% of a star's total lifetime. And so, also that is a long time in human terms. You cannot expect to find many stars in the protostar stage. And furthermore, protostars form deep inside clouds of dusty gas that absorb any light, and protostar might emit. Only when the protostar is hot enough to drive away its enveloping cloud of gas and dust, and can it finally be seen as the visual wavelength. The birth line in the HR diagram in this diagram, as you see in this slide, shows where contracting for protostars first become visible. Protostars cross the birth line shortly before they reach the main sequence. And you may see here in this slide. Also, and that means the early evolution of a protostar is hidden from sight. And also, astronomers cannot see protostars at visible wavelength before the protostars cross the birth line. Only see this birth line. Okay? And the forming stars can be detected in the infrared. The surrounding dust absorbs light from the protostar and grows warm. And warm dust radiates copious infrared. Infrared observations made by orbiting infrared telescopes reveal many bright sources of infrared radiation that are protostars buried in dust clouds. Study this observational evidence of star formation and notice 4 important points and 4 new tabs. And first of all, you can be sure that star formation is going on right now because you can find regions containing stars so young. They must have formed recently. For example, T-Tauri stars are still in the process of contracting. Second, visual and infrared observations can reveal small dusty clouds of gas called Vogue globules that seem to be in the process of forming stars. Third, in the HR diagram, newborn stars lie between the main sequence, as you can see from upper left corner up to the down right corner. Just where you would expect to find stars that have recently blown away their dust cocoon. And fourth, finally, observations provide clues to the process by which stars form. Disks around protostars eject gas in bipolar flow that push into the surrounding interstellar medium and produce Herbig Haro objects. Also, observations of small, dense cores of gas and dust within larger nebulae show how star formation begins. Star formation in a cloud of gas can produce lots of stars. But as soon as a massive star begins to shine, the cloud begins to suffer. The sudden blast of light and gas flowing away from the hot star blows the gas and dust away. and only the densest blobs of gas and dust near the star can resist. Like sunshade, the dense blobs protect the gas and dust behind them. And the result is star formation pillars that point like accusing fingers back at the massive stars. You can now recognize the pillars of the Eagle Nebula as star formation pillars, dramatic evidence of the formation of at least one massive star. All of these observations confirm the theories and that describe contracting protostars. Also, star formation will hold many mysteries. The general process seems clear. In at least some cases, interstellar gas clouds are compressed by passing shock waves, and the cloud's gravity, acting unopposed, draws the matter inward to form protostars. Now you are ready to visit one of the most active regions of stars formation, visible from Earth, a nebula you can observe yourself. On a clear winter night, you can see with your naked eye the great nebula of Orion at the farthest piece of Orion's star. With binoculars or small telescope, it is striking, and through a large telescope, it is a breathtaking. At the nebula center lie four brilliant blue-white stars known as the trapezoid, the brightest of a cluster of a few hundred stars. Surrounding the stars are the glowing filaments of a nebula more than 8 parsecs across. I hope you remember the distance of 1 parsec. Okay? Like a great thundercloud illuminate from within, the churning currents of gas and dust suggest immense power. The significance of the Orion Nebula lies hidden, figuratively and literally, beyond the visible nebula. The entire region is rife with star formation. But you should not be surprised to find star formation in Orion. The constellation is a brilliant landmark in the winter sky because it is marked by hot blue stars. These stars are bright in your sky not because they are nearby, but because they are tremendously luminous. These O and B stars cannot live more than a few million years. So you can conclude that they must have been born recently. And furthermore, the constellation contains a large number of G Tauri stars, which are known to be young. So Orion is rich with young stars. The history of star formation in the constellation of Orion is written in its stars. The stars at Orion's west shoulder are about 12 million years old, whereas the stars at Orion's belt are about 8 million years old, and the stars of the trapezoid at the center of the Great Nebula are no older than 2 million years. Apparently, star formation began near the west shoulder, and the massive star that formed the trigger and formation of the stars you see in Orion belt. That star formation probably triggered the formation of the star you see in the Great Nebula. Like a grass fire, star formation has swept across Orion from northwest to southwest. studied this star formation in the Orion Nebula and noticed 4 points. First, the nebula you see is only a small part of vast, dusty molecular cloud. You see the nebula because the stars born within it have ionized the nearby gas and driven it outward, breaking out of the much larger molecular cloud. Second, a single very hot star is almost entirely responsible for producing the ultraviolet photon that makes the nebula glow, and hot winds blowing from the most massive stars are inflating the nebula like fire. Third, infrared observations reveal clear evidence of active star formation deeper in the molecular cloud, just to the northwest of the trapeze. And fourth, finally, many stars visible in the Orion Nebula are surrounded by disks of gas and dust. Such disks do not last long and are clear evidence that the stars are very young. Note that these dusty disks are where planets form. In the next million years, the familiar outline of the great nebula will change, and a new nebula may begin to form as the protostars in the molecular cloud ionize the gas, drive it away, and become visible. Other centers of star formation may develop and then dissipate as massive stars are born and force the gas to expand. If enough massive stars are born, they can blow the entire molecular cloud apart and bring the successive generations of star formation to a final conclusion. The great nebula in Orion and its invisible molecular cloud are a beautiful and dramatic example of the continuing cycles of star formation. And now, let's come to some scientific argument. How do you think? What did Orion look like to the ancient Egyptians, to the first humans, and to the dinosaurs? How do you think? Scientific argument can do more than supports a theory. They can change the way you think of the world around you. So, the Egyptian civilization began only a few thousand years ago, and that is not very long in terms of the history of Orion. I agree with you. Nice, so you may produce your own conclusion. Today's hot young stars are a few million years old, so the Egyptians saw the same constellations you see. They call it Osiris. Even the Orion Nebula hasn't changed very much in a few thousand years, and Egyptians may have admired it in the dark sky along the Nile. Our oldest human ancestor lived about 4 million years ago, and that was about the time when the youngest star in Orion were forming. Your earliest ancestor may have looked up and seen some of the stars you see, but some stars have formed since that time. Also, the great nebula is excited by the trapezium stars, and they are not more than a few million years old. So your early ancestors probably didn't see the great nebula, right? The last dinosaurs died about 65 million years ago, long before the birth of the brightest stars in Orion. The dinosaurs, if they the brains to appreciate the view, might have seen bright stars along the Milky Way, but they didn't see Orion. All of the stars in the sky are moving through space, and the sun is orbiting the center of our galaxy. Over many millions of years, the stars move appreciable distance across the sky. The night sky above the dinosaurs contained totally different star patterns. The Orion Nebula is the product of a giant molecular cloud, but such a cloud can't continue spawning new stars forever. Focus your argument to answer the following. What processes limit star formation in a molecular cloud? Try to think about it. I think it's enough for today. And before the final, as usually, I want to ask you any questions or propositions. I hope you enjoyed this lecture, and I'm looking forward to seeing you next time. And some proposition and asking you may ask in internet too. Bye.